morning, everyone. My name is Rob Cassidy. I'm the director for the Center for Teaching and Learning at Concordia University, and also a seemingly lifetime member of SALTISE. So it's a great pleasure to welcome you all here today for a keynote speaker that I have been looking forward to seeing for quite some time. It's a real pleasure to be able to introduce our next keynote speaker. Manu Kapur is a professor and chair of the Learning Sciences in Higher Education at ETH Zurich in Switzerland. For those of you who are not familiar with ETH, it's one of Europe's finest universities. And there he directs the Future Learning Initiative, the topic of this keynote today. He's also a visiting professor at the NUS in Singapore, which is another prestigious university in Asia. Prior to that, Manu was a professor of psychological studies at the Education University of Hong Kong, and he's also worked at the National Institute of Education in Singapore as the head of the Curriculum, Teaching and Learning Department, as well as head of the Learning Sciences Lab there. I had the fortune of meeting Manu several years ago when he had just lit up the SALTISE community with his work on productive failure. I was therefore taken aback to learn that Manu has a bachelor's degree in mechanical engineering, 2 master's degrees in applied statistics and in education, and a doctorate in the learning sciences from Columbia University. He's also served as an associate editor and published in the most prestigious journals in the field of learning sciences. I thought, what a charlatan. Clearly this man knows nothing of failure. But as you can imagine, Manu is an in-demand keynote speaker at high-profile conferences and events around the world. So we're very fortunate to have him here with us today. And unlike many other learning scientists, Manu is driven to improve education rather than just understand it better, which is evident not only in his engagement with communities like SALTISE, but also in his work with major international government and advisory boards. On a more personal level, since I've had the fortune of meeting Manu previously, I was impressed by what an extremely generous thinker he is, and how he's always ready to engage deeply on these topics that are near and dear to the heart of us practitioners. And in those conversations, I was always impressed at the astute insight he can provide, the validation or even sort of expansive inspiration on our thinking that pushes us in new directions. So it's no wonder that we've asked him back here. This will be his second keynote at SALTISE in the last 10 years. So it's really exciting to have him here. And without further ado, he'll present his keynote on the Future Learning Initiative. So please join me in welcoming Manu Kapur.
Thank you, Rob. Thank you for that very generous introduction. It's probably the most generous introduction I've ever received. So thank you for that. I'll remember that for forever. It's good to be back. At SALTISE, well, not physically back, but virtually back, although I'd much rather be back physically, hopefully sometime in the future. So yes, I got to ETH Zurich in 2017, and the whole reason for my professorship, which was newly established at the time, was to jumpstart research in learning sciences in higher education. So in my career up until then had focused more on K-12 and some in higher education, but when I joined ETH, I made a commitment to working with other STEM scientists to do something about higher education, so learning sciences research in higher education. And so after 2 years or so of working with faculty, I put together this initiative called the Future Learning Initiative, won competitive funding for it, brought several departments together, and I'll describe some of the work that we're doing. Now, it's not very old, so not every project that I will describe will have findings already. Some I will describe, I'll share what I have, and in other cases, I will give you a flavor of what we're trying to do. And you will see the extent of the work. As I go through the presentation, you will also see that my orientation becomes more and more applied as I go. All right. So what is the Future Learning Initiative? It's basically our mission is to develop the world's leading center for research in the science of learning and advance ETH's reputation as one of the leading learning institutions. We have a strong core team, and we want to build on the strengths of this core team. And my colleagues and I put this initiative together to do precisely that. Very broadly, we have two main agendas, two main goals. One is basic research, and the other one is applied. So we want to understand the nature of learning across multiple interactive levels, all the way from neural to the cognitive to the embodied, social, and cultural mechanisms of learning. So full slate of basic fundamental research on learning. And we also are committed to developing applications and interventions in higher education contexts. Okay, so that's the goal. To put something like this together clearly requires a very, very big team. So we have a huge, almost 50 people, part of this interdisciplinary initiative. As you can see, it's very nicely gender balanced as well. There are more than 11 ETH departments. ETH has 16 departments altogether. 11 of them are already on board, both in terms of funding and time and work on the projects. We have more than 22 professors. Of these 22 professors, I think only about 4 or 5 are related to the field of learning sciences or educational psychology or cognitive science. Almost everybody else is a STEM scientist. So, and that's how, that's how we're positioning learning sciences at ETH, is that and the complexity of a learning phenomena requires that just learning scientists alone cannot investigate this. It's commitment to expand the fields that come into examining learning and the underlying basis of learning. And if we can understand that better, then we can build better applications. Okay, the project as a whole has multiple aspects. There are interdisciplinary projects to jumpstart research in the learning sciences in higher education at ETH. There's a PBL center, a project-based learning center, that's been set up as well. That's the second part. And for long-term planning, we have a new professorship on learning and technology in higher education. Today, I'm just going to focus on the projects component, the kind of research that we're doing in the projects that we have put in place. There are 4 major themes that have emerged in the work that there are. One, as you can expect, productive failure still continues. But it's not the main part of the work, but it still continues. And I'll talk a little bit about that. Embodied cognition and learning is a big theme that has emerged through the multiple projects. It was not designed so a priori, but when you start examining what are the latest issues or opportunities in research, then embodiment obviously cuts across those. And so we have a very strong program looking at embodiment in various ways. We also started research programs on ecologically valid assessments, moving away from resource poor to resource rich assessments. I don't think I will have time to talk about that in this talk, but if you're interested, we can always connect offline. And the final bit is AI and data sciences. Again, I will not have time to talk about that in detail. So I'll focus my talk today on the first 2 themes that have emerged. And there are multiple projects in these themes. And cutting across these things, as you will see, is this Venn diagram of overlapping circles. And all these indicators that any of these themes are examined at multiple layers of analysis or explanation. So neural, cognitive, embodied, social, and cultural. So on the top right hand of every slide, you will see which layers am I referring to on each slide. You don't have to follow that, but that's just a sense of where the projects are. Okay, so productive failure. I went back to my keynote slides from the 2013, I think it was, Rob, that I was in, that's 8 years ago. And I think that was a talk entirely on productive failure. And I'm not sure how many of you are familiar with productive failure, but the idea was I presented a lot of research at the time comparing direct instruction, which is the traditional way of teaching. That is, if you don't know something, you instruct the student, you explain to them exactly what and how to do something, followed by problem solving. And productive failure just inverts that and has certain features that are designed in the problem solving and instruction to make it really productive, right? So, and I compared, and I was looking at the summary slide of that just to see, even for myself, like what did I show 8 years and what have I been up to since then? So this is what I'd shown at the keynote 8 years ago. I had described a number of studies. I'm not going to go into them. I've described a number of studies, basically setting up the basic case for productive failure. and unpacking some of the key features and mechanisms through a number of studies. Some of those studies went on to find home in certain journals, as you can see, after the keynote. But that was my basic proposition at the time. It was all about productive failure and some of the underlying mechanisms. All right. What have we been doing since then? So it has so happened that productive failure has been now replicated across the globe. So we wanted to find out about a couple of years ago. I was working with my doctoral student, Tanmay Sinha, and I asked Tanmay, I said, hey, if you want to be true to productive failure, we've got to find out the boundary conditions. When does productive failure fail? So can we do an analysis of all the work that is in this genre, in this basket of problem solving followed by instruction, and compares it with traditional instruction or direct instruction, and look at all these experimental effects and what does it all say? So we took on a meta-analytic research. We compiled 166 experimental comparisons that compared problem solving followed by instruction with instruction followed by problem solving. Yeah, and we found that the average effect size in favor of problem solving prior to instruction was 0.34. Now, if this design, problem solving prior to instruction, followed productive failure principles, then the effect was almost twice the average effect. All right. So, and this is a paper that's going to soon come out in the Review of Educational Research. What this means is the productive failure has a very strong, just an average effect. But if you can design learning that is true to the principles of PF, which I'm saying here is high fidelity to PF, then the effect can be actually very large. What does this effect mean in real terms? I want to give you some benchmarks. So if a child spends 1 year with a good teacher in a math classroom and say they learn 1 unit of knowledge in that year, the gain is 1 unit in that year, then roughly speaking, productive failure has an average effect that is twice that. Right? But if you can carry out productive failure to high fidelity, then you can achieve an effect up to 3 times that effect. So what this meta-analysis just blew my mind. I mean, it was showing that on average, even on average, the effects are not incremental. These are quite astonishingly breakthrough effects. But if you're true to productive failure, if you can carry it out with high fidelity, you really stand to gain quite a lot. So that was something that came together over the last couple of years, just to get a sense of the research that's been happening in the past 15 years in this area. Right. So then, given the strong effect, we started asking the question: if the general effect, the high fidelity effect of PF is so strong, can we do PF in small doses? I'm sorry to bring in the analogy. It's like the vaccine analogy. Can you do PF in small doses? And maybe that has a very strong effect as well. And we wanted to test that. And in higher education context, one of the things that happens quite often, especially in large classes, and we deliberately wanted to target large classes because that's where you can make the most impact. If you can improve learning in the large foundational courses, you impact not only a large number of students, but if you make an impact in the foundational courses, then you have feed-forward effects on other aspects of their learning. So this was the first year linear algebra course for mechanical engineers. About 650 students take this course. And it's a very traditional lecture followed by a tutorial. So it's like instruction followed by problem solving. And it goes through that on a fortnightly basis. And you go through that, okay? And what we did was, and there was no degrees of freedom to change this basic setup. So what we designed was productive failure exercises, preparatory exercises at 5 points in each semester. So we asked the lecturer, give us 5 big ideas in this per semester, and just for those 5 ideas, we will design productive failure interventions just before your lecture. The total time that students engaged in these problem-solving activities over the course of the whole year was 7 hours. Okay, 1 year course, 7 hours of investment on the part of the student on top of the lecture and tutorials that they were taking, that they would otherwise have taken anyways. Okay, so 7 hour investment. This is a very difficult course at ETH. The historical passing rate is about 55% over the years. It's the same lecturer who teaches this for a number of years. So it's about 55%, which is relatively quite hard and low, right? So if I were to ask you, you have this historical passing rate of 55%. We designed a very small intervention that lasted only 7 hours total for the whole year. What would be a good percentage improvement in the passing rate? Now, obviously, I can't gather information from you right now, but I'm happy to report that we achieved in 2 iterations a 20% improvement. So we went from 55% passing rates to 75% passing rates. And if you look at this figure, the first box plot shows you the aggregate of the 4 years before the intervention started, and then the first iterations and the second iteration. And the effect of the second iteration, as we increase the fidelity, is exactly the fidelity of the meta-analysis, what the meta-analysis was suggesting. Right? So this showed that you can have large effects in higher education classes. If you want to align higher education with learning sciences research, it doesn't mean radical reform. It can also mean small, clever, strategically placed tweaks that can have large effects. So PF works in big doses, PF works in small doses as well. Then Tanmay, who was doing his PhD at the time, we started asking a more fundamental question. When you're doing problem solving followed by instruction, and in productive failure, we designed this problem solving deliberately to lead to failure because students do not know the concepts yet. So we asked the question, is failure even necessary? And so we carried out an experiment in the first year data science course at APFL, the sister university of ETH in Lausanne, in the French side. And the experiment went something like this. So students engaged in a problem solving on a data science problem in Python. And then this problem was designed that they would not be able to come up with the correct solution, and they didn't. Then after this initial episode, we gave them guidance. We said, okay, why don't you try a correct solution, a more optimal solution? Or we said, why don't you try another incorrect solution? We, of course, did not tell students that they were getting a correct or an incorrect solution. We just said, try this solution or that solution. But the experimental manipulation was some students were asked to try the correct solution, so they were guided towards that. And the other students were said, oh, you did not solve the problem correctly, try another incorrect solution, and then followed by instruction. And we had a control where there was no guidance at all, which I'm not showing here. Okay, and the basic finding was that deliberate guided failure. So the green, the red condition, incorrect, deliberately guided failure facilitates greater conceptual understanding and transfer relative to the success-driven, the correct scaffold or no explicit scaffold at all. So, in other words, it is better than even pure vanilla productive failure if you deliberately guide students to try even more suboptimal solutions than the ones that they generate. So failure seems to be necessary. We also collect data to find out that the benefits were mediated or moderated by, the need, the awareness that builds around the knowledge gaps that they have. Because the more incorrect solutions you try, the more you realize, many things are not working, and therefore that orients you to fill those gaps better. Okay, so that was another project. This project went further. We had recorded the videos of students engaged in these different conditions. And Tanmay actually developed a multimodal learning analytics screen to automatically build a pipeline to capture emotions of the faces from the videos and pass them through to analyze them, to make inferences about the emotional state, and then create, and then create two kinds of data. One is the emotion incidence data, which is an aggregate, different types of emotions aggregated per student, and emotion dynamics aggregate across conditions in the video frames. Okay, so, and then we looked at that. What were the key findings here? We, as yet, do not have any underlying basis or explanations for how emotions unfold in a productive failure environment. So what we really found here was that failure-driven scaffolding. Sorry, this thing keeps moving. Okay, what we really found was failure-driven scaffolding showed exclusive dynamics comprising shame. So students who were going through that, they exhibited facial recognition that could be associated with the emotion of shame, but this had strong metacognitive benefits. So it was not shame in the sense that we understand it, but that it was positively associated with metacognitive benefits. It also created, failure-driven scaffolding also created opportunities for greater displays of emotions. So there was a greater display of different kinds of emotions that went into that journey, which is understandable. Interestingly, the different kinds of emotions had positive correlations with outcomes. So hostile emotions like anger and disgust actually showed positive associations on the post-test learning, whereas contempt had a negative association with post-test learning. And not surprisingly, pleasurable emotions had a positive association with isomorphic post-test performance. So isomorphic problems that were on the post-test. These problems were similar to the ones that they had in their treatment condition. But pleasurable emotions had negative association with the transfer problems. So, again, goes to point that if you're having too much fun, it does not necessarily mean, if you're happy in the process of learning, it does not necessarily mean that you're actually learning. And conversely, if you're struggling and if you're feeling not quite happy or even angry or a bit of disgust, a bit of shame, but not quite content, then it can, when designed well, it can actually be very productive for learning. All right. And final, I think this is the final bit on the extra work and productive failure. One of my postdocs said, well, can productive failure work? It's shown to work for conceptual understanding and transfer, but can we make it work also for procedural knowledge? So she worked in the context of algebraic manipulations, algebraic manipulation skills, and this was actually in the schooling years. So this is not in the higher education context. And she built interventions for students learning how to manipulate algebraic symbols. And she found that even very brief 2 to 3 minute interventions of multiple iterative interventions could result in procedural gains compared to students who did not receive that. And she called that micro-productive failure. All right. So that was the bulk of the work since the last time I spoke at SALTISE, the basic work on productive failure and then where it has gone since then. Like I said, a second theme that has emerged in the work in the Future Learning Initiative is embodied cognition and learning. And here, there are multiple ways in which we are investigating this issue. So, starting with the very basic, concrete versus abstract representations, which are better and why. We're looking at the underlying physiological, neural, and embodied and behavioral dynamics when people engage in mathematical cognition. We're looking at embodied interaction from computer science and see whether we can design learning environments based on that. We're looking at neuro-embodied basis of how we come to develop intuitions in physics or physical phenomena. Haptic feedback, of course, is a very low-hanging fruit that we're looking at. And of course, a host of mixed reality and immersive and gaming simulations that design these embodied experiences. Now, I will talk about, these are several projects. Like I said, many of them started only a couple of years ago, anchored by doctoral projects and postdoctoral projects. So not every project is at a stage where I can share findings. I think the first couple of projects I'll go into a little bit more detail, and the rest I'll just give you a very quick flavor of. Right. So let's start with concrete versus abstract representations as a very basic question in embodiment. And I'm not sure if you remember, in 2008, Kaminsky and colleagues came out with a paper in Science basically saying, forget concrete representations altogether. If you want to teach mathematics, go straight into abstract representations. And those are the best. And they carried out 4 or 5 studies and showed that this was actually the case, that no matter how you configure, abstract representations always transfer better to new problems than concrete representations. And so, which was at odds with a number of learning scientists and how we thought about concrete and abstract representations. And this study was done in a higher education context. So if you go back, so we went back and looked at the study, and here was what the experimental manipulation was. They were teaching cyclical groups, and this were groups modulus 3. And in the abstract conditions, students learned using the symbols, as you can show. The circle, the diamond, and the flag. And these symbols students were learning these symbols, and there were rules for combining these symbols, which you can see at the bottom. So basically, if you know cyclical groups, this is how cyclical groups are. There are certain rules that they follow. And in this case, the flag was the identity. So that means that anything you add to it, it remains the same. Yeah, the thing retains the identity. So this was the abstract condition. In the concrete condition, they had three cups representation. Cups were either 1/3 full, 2/3 full, or 3/3 full. And as you can imagine, if you combine these cups, if you combine 2/3 with a full, then you have only 2/3 remaining, because the full basically makes no difference, at least as they argued. So they had these rules at the bottom, as you can see. 1/3 plus 1/3 will become 2/3, 2/3 with 2/3 will become 1/3, because you pour away the full part, and then the rest follows as well. So we thought this was really weird. The whole idea of having a concrete representation is that it connects with students' prior knowledge in some deep structural level, but also in terms of plausibility. And so we said, okay, we're going to just make a very minor change here. We're going to change the identity element, because that does not make sense to people in a concrete representation. Why would the identity element is a null element? So one would expect that the identity element should be an empty cup, not a full cup. So we just changed the identity element to a null cup. And another thing we changed was the storyline around it, because that was quite implausible. So we made just 2 minor modifications to this entire setup, and we carried out the experiment all over again. So I'm going to show you now what we found. So in the original study, like I said, they found that no matter how you configured things, the abstract training condition, as you can see, always outperformed the concrete training condition on abstract transfer problems. In the replication study, just by making those 2 minor tweaks, we were able to completely vanish the differences. So basically what turns, in our explanation, this study was, we published this in the Cognitive Science journal. And basically our conclusion was that the original science paper was not about the superiority or the advantage of abstract over concrete examples for learning. It was really poor abstract over poor concrete examples for learning. Any good teacher, learning scientist, will create good, plausible, well-connected examples to prior knowledge. And if you do that, you don't have any advantage of abstract examples for learning. We also carried out another level of transfer to formal mathematical knowledge. And there we found, in the same study, we found an advantage for learning from concrete, which was better. So overall, our conclusion was actually the learning with concrete examples is better. And that, we also concluded that, maybe it's not so useful to have this dichotomy between abstract and concrete, because we encode information that goes beyond just abstract and concrete. And that's the embodiment hypothesis, that there are nuanced interactions between how even concrete things are encoded. And we are designing further experiments to explore this further. For example, in some cases, we are actually going to get people to simulate mixing the cups and see what effects that has on learning these cyclical groups. Right. Another project that we're doing is we're going really full set into the underlying mechanisms. And here we're looking at the physiological, the neural, oops, sorry, it keeps going. Yeah, the physiological, neural, behavioral, and embodied basis of mathematics learning. Again, in this experiment, what we did was we gave people mathematical demonstrations. We're not calling them proofs because they're technically not proofs. They're just mathematical demonstrations to see and understand, okay? And a demonstration would be compute the sum of this infinite series, half, a quarter, plus 8. What does it add up to? For you guys, it must be quite straightforward. It adds up to 1. And there are different ways of proving that. And so our experimental manipulation was, we're going to give people different mathematical proofs. Some proofs are going to be symbolic. So these are the standard symbolic proofs. S equals the infinite series, 2S equals so much, which basically, once you shift the terms, this is a very standard proof. It becomes 2s becomes 1 plus s, and therefore s equals 1. Okay, so this is a very standard mathematical proof of this, or mathematical demonstration that shows what this infinite series adds up to. The math here is not quite as important for the non-math people. What is important is the math demonstration is entirely symbolic. Okay. Another group of people saw a geometrical or a pictorial proof. So you start with this whole square, then you divide it into half, then you divide the rest of it into half, and then you keep dividing the rest into half infinitely so, and you can see that the remaining black part, keeps reducing becomes infinitesimally small, so that without saying anything, people should be able to say, this means the series should converge to 1. Okay, so people saw either proof demonstration A or demonstration B. And our hypothesis is that these two demonstrations are going to be processed differently in terms of the neural basis of how people are going to process them. So we asked a number of questions in this study. Are there differences in brain behavior while processing symbolic versus pictorial math demonstrations? If so, what they are? Do these differences differ whether an expert is watching them versus a novice? So math experts versus non-math students watching these demonstrations. Are there differences? This is also a second order difference. Are there differences that differ by the state of the body, whether you're sitting down or standing? Because this is the embodiment manipulation. Whether understandings of these demonstrations, so after watching them, we got people to explain these demonstrations to the experimenter, as if that was the experimenter was a student, and we manipulated whether people could use their hands or not. And so we double crossed it, and we found, we haven't found anything yet, but that's the experiment. And then we are conducting a host of qualitative and quantitative analysis, both in terms of neural, physiological measures, and also behavioral measures and video recordings to be able to answer these questions. I don't have the findings for you yet, but this is one of the ways of some basic research that's being carried out in cognition. All right. This next project is a collaboration with the Department of Computer Science and the Game Technology Center. In the learning sciences, we have the idea of embodied cognition. In the computer science, there's an idea of embodied interaction. And we want to merge these two to say, okay, how can we design learning environments that help students understand abstract mathematics ideas, like derivatives and graph theories and linear algebra. So imagine you have gloves on and you can hold the curve, not just manipulate it, but hold the curve and then try to see how you can make the slope function coincide with the given function and so on and so forth. So same for graph theory and linear algebra. And there are studies, so one of the doctoral students, Julia Chartin, is carrying out this study where she's looking at, of course, qualitative understanding of what students go through when they are in these environments, and then carrying out a quantitative evaluation with different degrees of embodiment, where either students are just touching the graph or actually holding the graphs in virtual reality, and see what kind of learning can happen and how it prepares them for instruction that follows. So this is still in the problem solving followed by instruction mode. So it's kind of related to the earlier theme in terms of the logic of the design. But the experimental manipulation is the degree of embodiment. Again, we don't have findings yet, but that's an example of a study that we have. Okay, now the rest I'm going to go through pretty quickly because these are projects that are in the early stages. This is a project on physics intuitions. And here we designed a system where we're asking people to predict where the ball is going to fall. If there's an object going over and a ball is released from the object, where does it fall on the floor? There's a basket there that they have to position to indicate, this is where it's going to fall. And not surprisingly, many students or many participants have the misconception, the straight fall misconception. So they indicate it's going to fall down. Straight down, which is actually not true. So the question is, if so many people are exhibiting this, what do we do about it? So we're trying to design different manipulations. So maybe we get them to hold the basket to see where it's going to fall. maybe we get them to draw it out. Maybe we actually put their finger on the screen and make sure, and maybe those kinds of motor mediated actions actually develop more correct intuitions than just looking and inferring from the diagram. And while we're doing all of that, we're trying to understand the neural basis of this. This is the next two projects are in what happens at the nano level. So in quantum chemistry, for example, students have to learn these complex quantum molecular formulas and functions that they learn, and oftentimes their understandings of these chemical representations, the canonical chemical representations, are quite removed from the actual phenomena. In fact, I hear from professors that even professors don't quite understand what exactly is the representation. I mean, people create these representations. So the question here was, can we design a tool where students, instead of just reading about and visually seeing these representations, if they can manipulate the molecules in 3D space and actually feel the quantum molecular force in real time, so that there is a haptic component while encoding the force, maybe that will lead to better learning. And so this is an experiment that's going to try to understand that, things that you cannot see, but you can feel. And the chemistry professor here, Marcus Rye, had designed, and his group had designed a very nice tool that actually allows you to feel the quantum molecular force in real time. So it was a case of it was a tool designed to do good science, and we're using that tool to do good learning as well. Hopefully, we'll see how the experiment plans out. This is another example, but this time we're using HoloLens programmed to help students understand bioengineering, how to design bioengineering setups on a microchip, which they really can't see. And so the logic is the same, but it's in a different context of nanotechnologies. Here is a project on differential diagnosis. This is a more applied research, I would say, where we're taking a tool that takes medical students through medical diagnosis simulations with a patient, and we're trying to understand the effectiveness of those simulations on learning and transfer to clinical practice. And this, I think, is now we move into social cultural space and social cultural mechanisms here. And this is a project on ethics. Every research student at ETH has to undergo ethics training. And typically that ethics training is going to a course and trying to learn the principles and case studies, which is not too bad. And we thought, well, if you're going to learn ethics, we need to immerse you in day-to-day situations in research situations in the lab, where you actually have to make ethical decisions that have conflicting forces of personal time, family time, finances, relationships with others, and so on and so forth. So because ethics is not one thing, it's a complex dynamics of forces that come into play when somebody makes a call one way or the other, or in the gray area. And we wanted students to experience that in a game that we're designing for them. So this is a four-way collaboration between 4 departments to put all of this together, from the learning sciences to the ethics professors to the medicine and the computer science people. And we're working with architects to look at how space and cognition also interact with each other. And I'll just leave it there. So as you can see, we've looked, and all of these speak at some level, at the different levels, from neural all the way to social cultural mechanisms of embodiment, conceiving embodiment in different ways, and trying to find out the effectiveness of these interventions across these multiple layers. All right. Now, so that's the work that's going on. Now we turn a little bit of our attention to what I think is going to become more and more important as we take a turn to the future. All right, so this is the last part of the talk. Of course, as you know, AI is big. So one of the big things that's going to happen, of course, is artificial intelligence in education. Some of the work that's happening right now that's showing a lot of promise, whether it's perceptual recognition, pattern recognition, gameplay, text recognition, automated scoring, chatbots, and so on and so forth. These are very nice applications of AI, but this is what people in the field also call narrow AI. These are very well-defined, rule-bound, structured problems that AI can solve pretty nicely, and is getting better and better at. And I think these applications will come more and more. But there's a bigger challenge in AI, and that is the general AI, which the field is struggling with. And I think that's where the biggest advantage of AI would be tapped in general AI and personalization. And some of the work is only, we're only just starting, especially in a very unique way that, to train AI algorithms using what we know about human learning. So I think going from human learning to training AI algorithms is a neat way to work towards general AI systems. And so in this space, we expect to see a lot of learning sciences powered edtech supported by AI for personalized learning environments. Currently, there are a lot of promises of AI, but not much substance. But I think this will change in the years to come. More close and more immediate application of AI and machine learning would be in relation to the development of expertise, explicit and tacit knowledge. And as you know, experts have a lot of explicit knowledge. This is the knowledge that they can easily access, they can talk about, they can write about it. You hear textbooks and lectures and so on and so forth. But there's a lot of knowledge that's also tacit, that's difficult to access. Even if an expert tries to, it's hard to access. It's implicit, it's deeply internalized, it's situated, it's intuitive. And so, if the bulk of our focus in education is on explicit knowledge, then we know explicit knowledge can be codified. And if it can be codified, it can be automated and put to machine learning algorithms, right? So what this means is that if you're going into blended learning contexts, which we already are, but perhaps this will also stay in the future, then what is a principle we could use, or what is one principle we could use to orchestrate? How do you decide what to do when? And the idea is, let's use face-to-face presence environments for more tacit, coupling between the explicit and the tacit, while using the powers of technology and machine learning for the explicit components. I think that to me seems like a reasonable organizing principle for how we think about blended learning. Very recently, this is a paper currently under review, we did a meta-analysis of flipped learning research, and we ended up finding results that are highly consistent, not just with productive failure, but also with what I just shared. But this is still under review, so I'll wait until it gets published or close to publication before I say anything more. The second big thing that's going to happen is embodiment, and I've already talked a lot about it. The idea that mental and motor circuits are coupled, deeply coupled. Cognition and action are reciprocally connected. So the idea is that if you are not listening to the lecture and you are somewhere out on a terrace in Montreal, having a nice dish poutine with some beer or wine, what's happening right now in your brains is likely, your motor circuits are also being activated just by looking at this image. It's almost as if you're reaching out, although there's no overt action. And that's the idea behind embodiment as well. And we want to flip that idea to our advantage and say, hey, how does motor action, how does movement actually influence cognition? And if it does so, which we know it does, can be, moved to learn better. Can we move in ways that are better for learning? And of course, there's a whole body of research in the learning sciences. People like Martha Alibali, Mitch Nathan, and others have done a lot of work in this area, and we're just building off on that strong basis in the higher education context. But going forward, I think there's another convergence that's happening that will happen in embodiment, and that's with health and aging. A lot of the physiological bases, the basic biology in medicine are also encountering similar convergence between the body and the mind. And once these two have a strong connection, a strong coupling, learning sciences, health, and aging actually converge into joint research agendas. So research programs in higher education and lifelong learning, for example, would do well to conceive embodiment as a major research agenda that brings these two seemingly distinct or different fields together. And of course, the usual suspects of computer science and neuroscience and robotics are going to be there, as I've showed you in the many examples in the research that we're carrying out. Final area that I think is going to begin, and this is something that I've been thinking about it for a long time, and this is what I call learn agility. Learn agility. It's not an ability, it's an agility to learn, right? And the basic motivation is, there's a collapse of the demand forecast model. Means that things are changing at a pace where we can't forecast what is needed in the next 5 years, 10 years, right? So what do we teach? In terms of curriculum content, we have more and more content coming up. That's the job of science. And so the curriculum becomes more and more packed up, and we place bets on what kind of content is important, but that's not sustainable. The future of work is already here. I'm already in my 5th or 6th job or career. And for some reason, I've stayed in this one for a long time. But the idea is, you're preparing students for their first job, not necessarily their only job. They'll go through many different, so they need to learn and learn again. And so that requires that we focus not just on learning, but also on learn agility. And for learn agility, I mean in a specific way. And that is, if you were to ask yourself the question, when was the last time you learned something new, novel, something that was hard? So not something easy, but something that was hard, something that you needed to learn quickly in a timely manner. So you don't have a chance, I need to learn programming, so I will go to a course. Or I will go for a master's or a workshop at the university. No, you've got to learn it on your own or be resourceful about it. And how do you do that? So I think that's the kind of learn agility that I think is going to be important, and that's something that we need to design for. Now, this is a complex construct which has several components. I'm just going to list an initial set of sub-constructs, and to illustrate that, I'm going to share with you a case that we can all sort of relate to as teachers. Suppose you have A, B, C, and D, 4 students, just artificial, okay, just to illustrate the point. And you give them a test and say A, B, C, and D score this. This is the trend. D scores the best, followed by C, followed by B, followed by A, okay? Now you give these tests again and again, you paint a picture of the performance or the ability of the student in a certain domain. This is what we're used to, and based on this variation, we make all sorts of judgments and inferences, consequential, high-stakes inferences even, about what students can and cannot do, and where they should next be placed, and so on. What Learn Agility says is there's more to this entire disposition of the faculty that's important. And so suppose this is after this 1 hour test, for example, I give students another half an hour and say, I'm going to tell you that the items that you got wrong. Your job in the next half an hour is to correct them. So I give them an additional half an hour and I give them feedback. This feedback could be corrective and or explanatory. So it also explains if you wanted that. And then when told that they've solved a problem wrongly or incorrectly, students are given an opportunity to solve it correctly if they can. And maybe some of them are able to with that information, maybe more with the explanatory feedback. Suppose we give them another half an hour and say, hey, this time you can demand resource, just like you would do in an ecologically valid setting, where you can say, I don't know the stuff, so I think maybe I'll go and look for information. Or I need a computational tool or some tool to find out the solution to this. Or maybe I need to consult an expert or a peer or somebody who knows in this domain. And so say, I give you that chance to do that, and say the profile changes again. And you can design these kinds of experiments by giving students an opportunity to learn something new as well. And this new thing could be something that is close to the topic that they're learning or very far away from the topic that they're learning. And you can design experiments to look at how sensitive these profiles, these variations are based on the learning paths. Okay, so the basic idea here is that we're used to making judgments based entirely on the blues, but can we design a program of research and an underlying theory that starts to validate inferences around ecologically valid assessments that are more aligned with how things happen in real life, by making use of feedback, by making use of resources. And in the process of doing so, students develop the faculty to use feedback, to be resourceful, and to develop those alongside how we learn things, right? And give them opportunities to learn, right? So what we can already say that learning and learn agility are both path dependent. They're not something that happens, they're both path dependent. What we do not know is whether learning and learn agility are the paths the same. So the paths that optimize learning, are they the same as the paths that optimize learn agility? And so this is a classic case for a 2x2, right? So you have a learning versus learnability. On the x-axis, you have learning, low or high, just it's a broad category, and learn agility, that's low and high. So when learning is high, you're deep learning in a domain, but your learn agility is low, then what you might call these people routine experts. You know, Nano and Nagaki also dichotomize people along a different dimension, but they use the same term, routine expert. So we need routine experts in the field, obviously. You know, I want my airline pilot and my surgeon to be very strong in their learning, even if they can't drive a car or do something else, but they need to be very good in what they do. So we do need routine experts. But there's some experts who have deep knowledge in a domain, but they've learned this knowledge in a way that makes them very adaptive, that they can cross boundaries, they can learn new things very quickly, and therefore foray into and across these boundaries and deal with complex, novel situations quite innovatively. And that's what Hatano and Inagaki call adaptive experts. But there are also people who, you know, they have a shallow understanding, not quite deep, but a decent understanding of the field, but they're also very good at learning a lot of things about a lot of different fields. And, you know, sort of the jack of all trades, a generalist, so to speak. There's room for generalists, obviously, as well in the wider ecology. And I guess the area that we want to minimize is the low learning and low ability or low agility to learn new things, and that is underdetermined potential, or somebody who's just figuring things out, which is fine, right? But the idea is that that can also happen. So again, this is a very broad framework for learn agility, and I think we need to focus or start to shift design learning in ways that we're optimizing both learning and learn agility, design assessment in ways that we can create a strong theoretical and empirical basis for making inferences about both as we go forward. So with that, I thank you. And I'm not sure if there's any time left, but I welcome any comments or questions or suggestions, either here or after. Thank you very much.
Thank you very much, Manu. That was impressive. Yeah, so we do have some time, so we'll get some good use out of it. The question and answer has been very active, as has been the chat. So we'll have some limited time. So what I'll recommend for all of you tuning in is we'll alternate between the Q&A and some stuff that I've synthesized from the chat. So the easiest one to start off with is one of the most popular questions in the Q&A, which comes from Corey Legasic. And he's asking about whether or not you've looked at like student subgroups or student profiles within, you know, your productive failure model. I think was at the time, but you know, that can probably extend to other things. The question is, do you explore different groups' relationships to failure? So Scott Freeman, our previous keynote speaker, was looking at inequities in STEM and how gender, race, class could correlate differently to failure and motivation. Are there groups that will be impacted differently by being set up to fail in broader contexts of unequal opportunities?
Right, thank you. And that's such an important question. I have answers for two of the incoming differences. One is gender, and the other one is SES. Not SES, sorry. Students' mathematical ability or general ability as evidenced by a high stakes national exam. Right, so what we find in productive failure interventions is that students who appear very different on these national exams start appearing very similar in productive failure classrooms. And one of the reasons is very simple, because what failure does is activates their prior knowledge in ways that is relevant for what they're about to learn, which is something that they don't get in a direct instruction classroom as much. And therefore, they're able to bring more into learning from the teacher because of the productive failure. Whereas in a regular classroom, these differences actually perpetuate. Productive failure actually then mitigates or alleviates some of these differences. So I know that deliberately, it sounds counterintuitive, but deliberately designing for failure-based activation actually helps students understand what it is that they know, and then use that, even if it's incorrect, to understand what they're going to learn. And that's very powerful. So it actually helps. And the next bit about gender has a similar effect in productive failure. Gender differences typically get perpetuated in direct instruction classroom for the same reason. Small initial differences in prior knowledge actually amplify over time, because that's how the human cognitive system works, right? Whereas because productive failure deliberately activates knowledge, then initial gender differences also collapse a little bit. So those are the two main ones. My doctoral student is doing a more comprehensive latent profile analysis of incoming students, by clustering them according to the students themselves, not on variables, but on students, to design different clusters of students. And if you're interested in that work, then that's the work that I cited in the Journal of Educational Psychology that came out a couple of years ago. No, last year, sorry.
Very, very interesting. Yeah, I think that's something that's very interesting to keep in mind moving forward, is how differential effects can take place. The next one I'll come is a bit of a synthesis. Next question is a bit of a synthesis out of the chat. Specifically, I'm thinking of some comments made by Stefan Bracher, Alan Daguiar-Lopez, and Jim Katz, among some others. And it has to do with emotional aspects of productive failure. And then hopefully we can get a non-productive failure question in here. But I think what a lot of people were interested in kind of exploring a little bit with you or probing with you is, how do you get this right so that productive failure is not discouraging, what effects might it have on students' emotional, academic emotions or even personal emotions, and maybe if there's certain ways to help them understand the emotional sort of journey of failure and recovery to sort of set this up for success, if you will.
So this is about renorming. So one of the productive failure principles is about setting up the right expectations and norms, and I call it the social surround, together with my colleague Kate Blachek in the design paper that we wrote. And so, yeah, it's all about renorming and re-emphasizing and renorming and telling students that, when I give you this, when I take you through this productive failure experience, you're going to struggle, you're going to get frustrated, but I'm going to be there to support you. And if you're feeling frustrated, that's a normal space to be in. It's normative, not an exception. If you're struggling, that's normative, not an exception. If you're feeling sometimes angry because you didn't get the solution, that's also normative. And it's only when you get students in these spaces, in these safe spaces that you create for them, and then have also a support mechanism to say, yes, you felt that way, and then you learned how to deal with it. And I think these are things that we can also develop as part of designing these learning environments.
Cool, thank you. We're a little bit over, so I won't ask anyone, I won't ask any further questions, but there are some very interesting ones in the QA, so maybe we can discuss ways of getting some of those addressed. There's some mechanistic questions as well. But with that in mind, I just want to thank everybody for being here with us today. I want to thank our technical staff for doing a great job of keeping us up and running and keeping the subtitles going and all that sort of stuff. But most of all, Manu, I want to thank you. I want to thank you for being back with us. It's really a pleasure. Like you said, it's been quite a while since we've had you here, but it's always fun to have you here and listen to what's going on. Personally, as a person invested in higher education and this, I have to say I'm absolutely super impressed with what's going on at the Future Learning Institute. it's something really to keep an eye on. And I love to see that somebody's really engaging in higher education the way that you and your colleagues are, because it's as you know, in the learning sciences field, it's a quite peripheral kind of topic. So it's great to see that being engaged and engaged so intelligently. I look forward to seeing all the different things coming out there and potential, you know, interesting partnerships in the applied aspects of your thing. So thank you again for being here. I'm not sure what's next on the agenda. I'm going to turn it over to Sueli, and she will fill us in.
Thanks, Rob. Hi, everyone. Thanks, Manu, for the great talk. Now I would like to invite the audience to the award ceremony that we're going to have in Gather Town. The link I just put in the chat, so you can click on the link. You'll be sent to the Gather Town world. You can create your avatar and meet us in the auditorium. If you need help, you can find some volunteers here and there. They're going to be renamed, like their first name, Help. You'll see they're volunteers. And you can, they're going to guide you to the auditorium if you need any help or a tour over the Gather Town world. So thank you, and we'll see you there.